In this video, we're going to finish the last few questions on this table here to make sure we understand the concept. So we're starting from BR2 and then making our way down all the way to neon. So we're going to take a look at what type of forces would exist in the molecules within the table. So we're going to start off with BR2, and it's the same steps that we've been doing for all the other problems. We basically draw the molecule out if we can, and then figure out if it's polar or nonpolar, and then use the chart above to figure out what type of forces would be in there. So let's go ahead and do BR2. So BR2. And so if we draw it out, it looks something like this. It's a linear molecule. There's only two atoms there. Also, it's a diatomic molecule. Br and Br have the same electronegativity value. That's supposed to be a delta. I don't really even have to go to the periodic table. I just know that the difference in electronegativity is going to be zero. It's an equal share. So because this is linear, there's only two atoms, and it's a nonpolar bond, the whole molecule itself is going to be nonpolar. There's no ions. I know that because it's just two nonmetals as opposed to a metal and a nonmetal. So we're going this direction here where there's no ions because it's molecular. And then are there polar molecules? Well, no. And so we're going over here to dispersion. So there's really only one type of force in BR2, and it's London dispersion force. Let's go ahead and try ICL. ICL. Oops. So it's the same idea. We're going to draw the molecule out, and then we're going to try to figure out what type of forces exist within ICL. So here we go. So we have ICL, and when we draw it out, it looks something like this over here. This is a Lewis structure, and this is not that's a dot I put by accident there. We want to figure out if it's polar or non-polar. We know it's going to be a linear molecule just because there's only two atoms there. So let's go ahead and take a look at the electronegativity difference between these two. So I is 2.5, CL is 3.0. So so we have the electronegativity difference is 2.5. Whoops, we don't want a negative value, so I should put the larger value there. So 3.0 minus 2.5, 0.5. So we are slightly polar. And I think we said that chlorine is more electronegative. So the partial charge will be, negative charge will be on the chlorine, and partial positive charge will be on the iodine. So it is slightly polar. So let's go ahead and take a look at our flow chart here. We know it's an ionic compound, so it's not going to have, it's a molecular compound, so it's not going to have ions. So we're going this direction. Are there polar molecules? Yes. Are there any HN, HO, or HF? No. So we're really at the dipole-dipole area. So it's strictly dipole-dipole, pretty weak one, but still there. Also LDF, don't forget. The strongest force here is the dipole-dipole, because LDF is the weakest of all. For O2, we can figure that one out pretty easily. It's similar to BR2. So remember O2, if you were to draw it out, you'd have a double bond here like this, like this, like this, like this. And the electronegativity difference between, well, two O's there is zero. There's no central atom. It's linear, so we're good. And so what I would do is I would, because it's nonpolar, we know the only force for nonpolar is the London dispersion force. So LDF is the only and strongest force within that molecule. We can try CH3Cl. So for CH3Cl, I would draw that out. You could figure out its shape, which is tetrahedral. And then we'd have to figure out if it's polar or non-polar. So are there polar bonds? Well, you're doing the electronegativity difference between a variety of these. Here, the electronegativity difference is 0.4, 0.4, 0.4. So those are non-polar bonds. But let's take a look at the CCl bond. So for CCl, we have 3 minus 2.5. So 3 minus 2.5 delta En for the Cl bond. 3.0 minus 2.5 gives you 0.5. And so yes, that is polar. So there are polar bonds. Two Are there lone pairs around the central atom? No, there are no lone pairs around the central atom. Um, so the next question we need to ask ourselves, though, is are all the molecules, are all the atoms surrounding the central atom the same? And they're not the same. So because they're not the same, this is not symmetrical. We have a partial positive, partial negative charge in the Cl and partial positive charge on the left side of that molecule there. So this overall is polar. And I'm just going to put that the atoms are not the same because you have CH, 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 and CCl. So it's not symmetrical. So this is polar overall. So we're dealing with a polar substance. We're not dealing with ionic compounds, so there's no ions. Are there polar molecules? Yes, it is. Are there any HN, HO, or HF? No. So we're dealing with a dipole-dipole interaction strictly. So this is a dipole-dipole interaction, not a hydrogen bond. Don't forget, though, there's also LDF, just like in every other molecule. Let's go ahead and try HCl. So for HCl, when you draw that out, it looks like this, HCl. It's linear, and if you do the delta En between Cl and H, you'll do 3 minus 2.1 is 0.9. So that there is considered polar. And the electronegativity of chlorine is higher, so the partial negative side is where the Cl is, and partial positive is where the H is. So we do have a polar molecule. It's 0.9 electronegativity difference, but it's not ionic. So we know that there's no ions present. So we're going this way. Polar, yes, but are there any HN, HO, or HF? No. So it's not hydrogen bonding. It's very easy to be tricked with that, but not hydrogen bonding. It's just dipole-dipole. And don't forget, there's also your LDF in there, but the strongest, oops, I think I made a mistake in a previous question also. The strongest for both of these is not LDF and LDF, it's dipole-dipole. It's stronger than LDF. I don't think I made that mistake anywhere else. If I did, you would have spotted it and you would have been confused and you would have emailed me, asked me about it. So if I do, you can always email and ask. And if you're confused by a wrong answer, it means you understand. So that's good. So that's HCl. Let's go ahead and finish with the last one, which is Ne. So Ne is just an atom. It's not a molecule. It's just an atom. It's neon. It's neon gas. It's a noble gas. And noble gases are room temperature. Well, you guessed it, they're gases. So this is Ne. So it doesn't really make sense to ask if it's polar or non-polar because there's nothing else it's attached to, right? Polarity really means a difference in electrons between two atoms or between two parts in a molecule. Now, you can still have polarity in an atom by itself, though. And what I mean by that is you can have some areas around the atom where you have some slightly partial positive charges and partial negative charges. Because remember, the electrons are always moving around. So sometimes you have these instantaneous dipoles that might develop. And then they develop in other places, but it's just they're always moving around. So if you see a single atom like this, generally, that's a gas, like a noble gas, the only thing it can really have is dipole-dipole because of those little temporary charges that develop. But it can't really have anything else. It's not a polar thing. There's no permanent charges. There's no permanent dipoles or partial charges. So a single atom like this is just going to be LDF. There is a little exception. I just want to mention that. And here's why. Neon is a gas at room temperature. The noble gases are because, well, they're atoms that only have noble gases. But a lot of metals at room temperature are solid. So, for example, if you look at magnesium, you might have seen it as a little strip of magnesium like this, and your teacher maybe burned it and you saw bright light. Magnesium, if you write that single atom down, it's a solid at room temperature as opposed to a gas like neon. And so you think, okay, well, wouldn't this here have only LDF? So shouldn't that be a gas like neon? Well, metals have an additional thing called metallic bonds. It's an intramolecular force you learn about in grade 12, but they basically kind of share all their electrons in a group of atoms, and that gives them a bit more strength and allows them to be solid at room temperature. So metallic bonds exist within metals. So if you have a sample of metal like magnesium or copper, they're further strengthened by their metallic bonds. There's also LDF there, of course, but again, further strengthened by metallic bond. But that's more beyond the scope of the course. You do know it now, so you can explain that idea. But we have neon there with only LDF being in its gas state. And so that is just going over the different molecules and finding what types of forces there are in there and labeling the strongest force. And you need to be able to do this to identify the forces so you can then predict properties or compare substances and decide, which one has a higher boiling point or lower boiling point, which one is soluble where, and so on and so forth. So that there is our lesson. And I highly recommend you do you redo these problems if you need to, and also do the practice problems in the worksheet.